Welcome once again to RF transceiver design course. We are discussing about stability and amplifier design. So, for stability, uh, what we have done in the last lecture, if a two port network is available and if there is a S parameter that we know after the biasing of the circuit, if we know the S parameters, based on the S parameter we can find the input and output stability circles, and that circle will tell us that where should we how should we do the input or output matching. So that we could not have a unstable. So your amplifier will not be a potentially unstable. So that is called a potentially unstable, and when you have a stability, it is a stable that our amplifier is a stable. Now there is another method also, considering the, let us say there is a circle we have drawn, stability circle, that is a one method. By using equation also you can find out that there is a your system or amplifier is unconditionally stable or potentially unstable. So, for that there is a K delta test or a mu stability test. So, there are two equation, that is K and delta. So, if you know the S parameter and if you put in this equation, that is a K and this is a delta. So, if K is greater than 1 and delta is less than 1, so that is a your system is unconditionally stable. If this is less than 1 and if this is a greater than 1, then it is a not unconditionally stable, it is a unstable system. In mu stability test, there is a, here in K delta you require two equation. However, in mu you require only one equation. This one equation, if your mu is greater than 1 for entire frequency range in which you want to design your amplifier, then it is a unconditionally stable. So, the advantage of mu test is that only a single parameter needs to be evaluated. There are no auxiliary condition like K test, derivation earlier and then delta test. So, this is a methodology by which you can also find the your system is stable or unstable. And when you draw the Smith chart, because in the Smith chart you have advantage that you are also going to use a Smith chart for impedance matching, you can easily correlate the Smith chart. So, this is the two ways of doing impedance matching or finding the stability. Now, we will move to the power gain equation, and this is useful in the any amplifier design, micro amplifier design or high frequency amplifier design. If you are designing on chip also, only the here the there is a two port black box is there. Now, this two port black box can be replaced with any transistor. It can be GaN or it can be gas based transistor. We already have discussed the multiple technologies by which you can make the active components. It can be a transistor network also. Let us say for example, you have a cascode. So, this is some bias you have given, there is a input and this is a two transistor network. There is a output is also there. So, this output can also have a bias T. So, there is a biasing you need to apply here, and you can also get the S parameter of this transistor network. It can be differential amplifier also, but you should prior simulated or you should know the S parameter of your network. If you know the S parameter of your network, you can find out the power gain equation. So, what is the aim of amplifier design? Let us say you have identified the transistor network or a transistor, then what is the aim? How to select gamma S and gamma L, reflection coefficient at the source side, that is this, and reflection coefficient at the load side, that is that gamma L. How you have selected gamma S and gamma L at a given frequency to design the input matching network and output matching network. So, this is called a IMN, that is input matching network, and OMN, that is a output matching network. So, this is your transistor or transistor network. This is a gamma S, there is the gamma in. So, the here the this is a gamma S on this side. So, it will be something like this, and then gamma in. So, gamma in, that you look from this side, that is a gamma in, you look from this side, that is a gamma out. So, what will happen when you find out the gamma in? We already have find out in the last class by using the Mason semantic rule, that how to get the gamma in and gamma out. Once you, because gamma in is depend upon the gamma L and gamma out is depend upon the gamma S. So, our aim is to design the input matching network and output matching network, and there are different power gain equation based on what you are considering. You are considering the completely input side, considering the source, or you are considering the completely output side. So, by that we can define the power gain equation. So, these are the amplifier gains. So, this is a figure of different figure of merit to assist in amplifier design. So, the first gain is a GP, that is a power delivered to the load divided by power delivered to the network. So, that is given by PL divided by P in. So, here you will have you should consider only the this much portion, that is a load side and the network. Then GA, that is a power available from network and power available from the source. So, that is a you will consider this side of the amplifier. And GT, it is the ultimate figure of merit, or it is the power delivered to the load. You are considering the entire circuit and power available from the source. So, this PL by PAVS will give the complete amplifier where the source is also considered and the load is also considered. Now, we will try to derive the each parameters by using the signal flow graph. So, before going for the find out the each parameters, we will first find the B2 by A1. So, that is a T21. What is the transfer function for T21, that is a B2 by A1. So, how to find out? So, in order to get T21 which is equal to B2 by A1, so you need to make the signal flow graph. So, signal flow graph, once you have made, you can find out how many paths and how many loops are there. So, if we see the network, if we try to draw, that is this is A1, B1, B2, A2, these are the nodes. So, always signal will travel from A to B. This is S21, S12, S11, S22, and because there is a load, you should consider the gamma L. So, if you want to find out the B2 by A1, how many paths are there? So, there is only one path, that is a S21. So, there is only one path S21. How many loops are there which is non touching to the path? There is no loop which is non touching to the path, that is why delta 1 is equal to 1. Delta 1 is equal to 1 here, and you will have a delta, because there is one loop S22, gamma L. So, 1 minus S22 into gamma L. Once you put in this equation, you will have B2 by A1 S21 by 1 minus S22 gamma L. So, this is the way you should find out the transfer function by using the Meson semantic rule. So, now we will use this B2 by A1 this equation in order to find the various power gain. So, the first is the power gain Gp, power delivered to the load divided by power delivered to the network. So, power delivered to load PL is given. So, this is a network that we are going to consider. There is a gamma L. So, power delivered to the load is given by this, and power delivered to the network is given by P in. So, you can directly write B2 square minus A2 square. While discussing the S parameter, we have already discussed that you can represent the power in terms of B and A, incident and reflected wave. So, this is a B2 square minus A2 square. Similarly, you can also get the input power, because there is a input, that is A1 square minus B1 square. Once you take out B2 and A1 common, there is 1 minus A2 by B2 square, 1 minus B1 by A1 square. So, B2 by A1 square we have already find out, A2 by B2, because here when you consider this gamma L, your gamma L will be like this, which will be from B2 to A2. So, you can get your A2 which is equal to gamma L B2. That is why A2 by B2 is equal to gamma L. So, that you replace here, and at the input side your input reflection coefficient is given by B1 by A1. So, that is gamma in square. We already have derived B2, that is S2 1 square by 1 minus S22 gamma L. So, we just replace this, which is a T21 that we have derived in the last slide. So, this is a Gp power gain equation, which is a power delivered to the load and power delivered to the network. We will see there is a specific application to consider this power gain. Now, we will move to the another equation that we are going to derive, that is what is the attributes of the power gain. So, for matched loads you can consider gamma L which is equal to 0 and gamma in which is equal to S11. The power gain, that is 1 by 1 minus gamma in square, S21 square 1 minus gamma L square, here S22 into gamma L. So, if you make this as a 0, this term is a 1, this is also 0, then you will have S21 square 1 minus S11 square. So, for lossless device, if you have a Gp which is equal to 1, we have the power conservation relation S21 square plus S11 square which is equal to 1. So, this is also satisfying the power conservation relation, and it can also, it is widely used for a power amplifier design where output impedance is more important. So, this Gp gain is considered when you have a output impedance matching is more important, and your gamma L that you need to find out. Then we will go to the transducer power gain, that is a Gt, which is a ultimate figure of merit Gt, that is power delivered to the load and power available from the source, equal to PL by PAVS. So, power delivered to the load RMS value you can directly write B2 square minus A2 square, you will get B2 square which is equal to 1 minus gamma L square. So, how do we get the power available from the source? Same, we will try to get, this is a ZS and then ZS conjugate if it is match. Then from this there is incident wave signal A1 and reflected is a B1. You can directly write A1 and B1. So, there is a gamma S conjugate and gamma S. So, Bs, that is a source to the signal will travel to the A1 and then A1 to A1. So, there is only magnitude 1 in order to find out the Bs by A1, A1 in the relation to the Bs. So, what is the A1 here? A1 we can directly write A1 is equal to Bs by 1 minus gamma s square by using this signal flow graph, because there is only one loop, that is gamma s square, there is a one path, that is Bs. So, A1 by Bs, that is 1 by 1 minus gamma s square. So, PAVS you can write A1 square minus B1 square, which is equal to A1 square 1 minus B1 by A1 square. A1 square you can replace with this equation, that is 1 minus gamma s square whole square, and there is a 1 minus gamma s square, B1 by A1, again it is a gamma s square. So, this will be cancelled out and you will have B s square by 1 minus gamma s square. So, here gamma s is less than 1. So, that is why we can directly cancel this. So, transducer gain then finally written as a B2 by Bs 1 minus gamma L square into 1 minus gamma S square. So, here gamma L square based on this equation. So, when you take a B2 square, that is 1 minus gamma L square. So, this is the GT. Now, we try to we will try to find out the B2 by Bs. So, now important term is a B2 by Bs. So, how to find the B2 by Bs? We first draw the signal flow graph. So, this is a signal flow graph for the same. This is Bs A1 gamma s S11 S22 gamma L S12. We have made the signal flow graph. Now, how many paths are there from B2 to Bs? There is a only single path. If you want to reach to B2, that is only single path S21. And how many loops are there? There are 3 loops and 2 are non-touching loops. So, one is gamma S gamma L combination, another is gamma L S22 combination, and then third is a gamma S S21 gamma L S12. So, we tried to consider all these 3 loop in the transfer function. So, that is a P1 delta 1 by delta 1 is equal to 1, because there are no non-touching loop, all the loops are touching to the path. So, that is S21 divided by 1 minus the first loop, that is gamma S into S11, then second loop S22 into gamma L, and third loop, that is S12 gamma S S21 gamma L S12. So, this is a third loop. So, 1 minus gamma S S11 plus S22 gamma L plus gamma S S21 S12 gamma L, plus because these two are non-touching loops. So, you can multiply, that is gamma S S11 and gamma L S22. So, here straightforward we have tried to use the Mason semantic rule, and if you work out this equation, B2 by Bs square 1 minus gamma L square into 1 minus gamma S square equal to 1 minus gamma S whole square. So, only the thing is you need to replace this. If you rewrite this, and it is a straightforward, you can and if you consider gamma in or gamma out equation, you will get 1 minus gamma S square by 1 minus S11 gamma S S21 square 1 minus gamma L square by 1 minus gamma out gamma L whole square. So, this is the way you can find out the transducer gain, that is GT. It is a ultimate figure of merit for the power gain. So, what is the attributes of power gain? Here you are if you are considering the gamma L, which is gamma out conjugate, then it is a power available from network. So, this is a GT PL by PAVS B2 by Bs square 1 minus gamma L square 1 minus gamma S square. If you consider that your transistor is a unilateral, where it is S12 is equal to 0, in that case you can consider gamma out which is equal to S22. So, in unilateral, that means you do not have any power flow. So, here this from A2 to B1 there is no power flow, means you have a very good isolation between input and output, and S12 is equal to 0. So, if you consider S12 is equal to 0 in this equation, you will have 1 minus gamma S S11 minus S22 gamma L plus gamma S S11 gamma L S22. So, you can easily write this as a 1 minus gamma S S11 1 minus gamma L S22. So, this gamma out will be replaced with the S22 if you consider the S12 is equal to 0, that is called a unilateral case. So, or if you can also consider the gamma out which is the gamma L is equal to whole square. So, what is the property? Your GT is a function of S parameter of your network, transistor network. It is a function of gamma S, what is a source reflection coefficient, gamma L, what is a load reflection coefficient, and both source and load impedances. So, it is a function of all the parameters available in the transistor network. So, if you have a gamma S, gamma L is equal to 0, that means if it is a match to the S11 and S22, you will have a GT which is equal to S21 square for gamma S and gamma L is equal to 0, because if you put gamma S and gamma L is equal to 0, you will have a GT S21 square. Now, power available power gain, you can also get GA, where power available from the network PAVN and power available from the source PAVS. So, only the difference in power available from the network, if you consider gamma L is equal to gamma out conjugate. So, you can directly replace in the GT this gamma L is gamma out conjugate. So, gamma out square, you can directly write this available power gain equation. So, here GA is as function of gamma S, and because there is a source is more important, and we already know that for low noise amplifier you are going to connect antenna when we have discussed the different transceiver architecture. The first component is a low noise amplifier and its input impedance should be matched with the antenna. So, input side is more important, and in that case this GA is a function of gamma, and as your output is already matched. So, it has a good application, this GA has application in LNA design, and GP, as I told, it has application in the power amplifier design, where the load output matching network is important, because we are going to connect the power amplifier with the antenna, output of the power amplifier with the antenna. So, this is all the gain formula that we have considered. So, if we summarize, this is a transistor network. So, there is a 2-port transistor network, and here there is a input reflection coefficient, output reflection coefficient, that is important, GT. This is a transducer gain, GA, that is available power gain, means and GP, that is a power gain. So, these all are the figure of merit, and we can try to use it for designing the amplifier. Now, how to select gamma S and gamma L at given frequency. So, if you want to design an amplifier, how you can design an amplifier. So, when you want to design the amplifier, our focus should be in this section will be on achieving a specific gain target. What do you want? Do you want a maximum gain GT or specific gain GT which is less than GT max, or other possible targets to discuss are the minimize the noise, because that is related to the gamma s. When we see the low noise amplifier, we will discuss more in detail the gamma s, or how you can find the optimum value of gamma s. Then maximum output power P1 dB, we need to have a design specific gamma L, so that you will get the maximum output power P1 dB, and it has application in the power amplifier, and we need to check that the device is stable. For this gamma S or gamma L selected, how do we obtain the maximum gain? So, our target is to find the maximum gain of the amplifier, and you can use all this gain formula and stability criteria in order to find out the value of gamma S and gamma L required to achieve the necessary gain or a maximum gain. So, in this lecture we have discussed all the gain formula. In the next we will try to design the amplifier by using this formula. So, thank you. We will discuss about the amplifier design in the next lecture.